So I'll give you examples to show that this computation principle is. So for instance, let's look into examples now. First, yes or no? Yes, it is. Okay? It is. Right? No.
Because of the x squared.
Yes. F of minus 1 is 1, which is not. F of 1 is 1. And f of minus 1 is also 1, which is not minus 1. Minus of f1, right? So the third stage that drops off. Okay?
Sorry, sir.
Yes.
I'm just missing something. What are you checking now? What are you applying? The first law, where you like number 1. What did you check first?
Well, over here, both the domain and codomain are vector spaces.
Okay.
F of 0 is still 0. F of minus of x is minus of f of x, that we can see. So now I have to do that strange big check. So I do x plus lambda y, and I come up with this. I actually don't produce these two in my answer. These two. I immediately say that these two are vector spaces and it satisfies this, and therefore this happens. Okay? I produce this check. But wait. But here, in this case, I see both the domain and the codomain are vector spaces. But I can immediately see f of minus 1 is not equal to minus of f1. So it is, I do not do any further check. So it is not a linear transformation. I don't do those checks. It's just about, you get into the habit of finding whether the domain and codomain are vector spaces, whether these conditions are satisfied, this one and this one. If not, just say it and you stop. Yeah.
So is it necessary when you in exam, whereby, for example, number 2, it's a vector space, but codomain is a domain, but then the last one is not. So is it necessary to write all those three?
No, you just say the domain and the codomain are vector spaces, but this is not true. Hence, it is not a vector linear transformation.
Then you have to do that.
That's it. Yes.
Excuse me, sir.
Yes.
Sorry. On checking whether the codomain and the domain, or the domain and the codomain are vector spaces, are you just looking at in other words, the real numbers, this one is also real numbers, then they are vector spaces. Is that how you're concluding?
Yes.
Okay.
Yes,
what would be an example where they are not vector spaces?
Well, slowly I'll come.
Okay.
This one is a little bit notorious. Domain and codomain is, both are vector spaces. F of 0 is 0. F of minus x is minus over x. Right? So, the only way left is to show that this one, the last one. So we have to show. Let's look into this. F of x plus lambda times y, which is f of x plus lambda y cubed. This I know. And this okay? So, for instance, for example, 1 plus, or you can say, sorry. Yeah, 1 plus lambda cubed is not equal to 1 plus lambda cubed. Okay? If okay? So that stops you. Okay? So answer is still no. Okay? Sometimes even those little checks maybe the function may be cleverly set. Yeah? Okay? Now let's come to another example. Yeah?
Just previous one, please, sir.
Yeah, just thank you. Thanks.
Would be a bit crazy to start thinking that x to the n is obviously to go up, it's unlikely to be 1. Probably to prove it.
Yes. Yes. Correct. Correct. As n is not equal to 1, it is no more a linear transformation.
So we're spending a lot of time improving what is linear and what is not linear. I mean, if it's not linear, does it imply that there's certain operations we cannot apply to it?
No, it just means that the function may be interesting, but as far as our vector space is concerned, it is not preserving those vector space structures. So it is not important as far as study of vector spaces is concerned. Okay? It might be important somewhere else. That's a different story. Okay? Yeah.
Sorry, sir.
1 minute.
Sorry. Excuse me, sir.
1 minute. Coming back. Yeah.
So I'm saying, put number 3, example number 3, I think your own equation to prove that the third statement is not again. For example, the proof that we just proved right now.
Yeah.
So can you come up with your own equation to prove that this is not actually a
Yes. You definitely should. Yes. Okay. Yes. Your question is Bloemfontein. Yeah. You're from Bloemfontein, right?
No,
Okay,
no.
go ahead, carry on.
I'm in Pretoria.
Oh, okay. Yes.
Yeah, on number 3, I just want to check something because we are what you're proving there, which is the third one, like if it preserves f of x, lambda f of y. Now, on this particular example, how are you matching that structure of f of x lambda f of y with the x cubed plus y cubed?
Well, this is what? X cube is f of I'm sorry. There should be lambda cubed y cube. Sorry, there was a mistake here. Yeah. But x cube is f of x, and lambda, what is my mistake here? Again.
Okay.
There was a mistake here. It should be lambda cubed, and what I wanted to show is not this. That is this. Right? Okay. Clear? Now
Yeah.
let's have another one. Why? The codomain is not known to be a vector space.
Codomain or domain? Codomain.
The codomain.
The first one, I can understand the second equation of x mapping to sin x. Sin x is not a linear equation, but that you're mapping a real number to -1 and 1 through a function. So how do you say now that -1 and 1 is not a vector space, or not to be a vector space?
Yeah. Well, we didn't firstly cover this, -1 and 1, we didn't show, right? In fact, with the usual, if we take the usual addition on rails, it is never going to be a vector space. Because if I take half, then 20 times half is not there. Okay? So under the real addition and real usual scalar multiplication, it is not a vector space. But who knows whether there exists a separate addition. And well, if that is the case, then, well, this was actually in that sense, a very bad question, until and unless someone specifies the fact that I make -1 a vector space in this way. That's a separate thing. Okay? So that's why I said it's not known to be a vector space. All right? What about this?
Just one step back at number 4. -1 and 1 are possible results for sin x.
Everything between -1 and 1 are
Possible results for sin x.
yes. So this is a surjective function. Yeah? So, now, what about number 5? Huh? Yes, it is. Yes, it is. Because I can see immediately effects of this. Right? And, yes. Remember, as I said, number D, condition D. That's equivalent. Right? So this is immediate. Let's have another one like this, then we go for much more general kind of results. So it looks so. So you check. I leave it to you. So actually, you see, now we are getting more and more difficult examples, and we really have to do all this check. So we need to find out ways and means to get hold of linear transformations. Okay? All right. So here is our next example. If yes.
You said R3, R2, but you were X, Y, Z.
I'm sorry. Thanks. Okay, sorry.
Hello, sir.
Let's get from 5.
Hello.
Yes.
Yes, sir. Can you please go to example number 5 and 6 and repeat the explanation again, because I'm a little bit confused with the way you did it. Even how do you know on example 6 that instead of being y plus z, it's y minus z, because we are moving from a vector in 3 space to a vector in 2 space. Can you please just repeat those examples?
Well, there was a mistake. Firstly, in writing 6, the output cannot be a 3 vector, it has to be a double. So that was my mistake. And now about this checking, well, that's what I remarked. I left it to you to check that both 5 and 6 are indeed examples of linear transformations.
Okay.
Yeah. You have to check this, but it is now clear that with more and more difficult examples, the checks might be very, very tedious. Okay?
Yes, sir.
So we need some kind of a mechanism to recognize linear transformations immediately.
Okay, sir.
That's what we are trying to proceed now.
Okay.
All right. So if V and W are vector spaces, then these projections are also linear transformations. Okay? I'll do one of them, and you can do the other one. The proof is very simple. Let's do the first one, phi 1. Say x plus lambda times x prime y. This is obviously x plus lambda times x prime, but x is pi 1 of xy plus lambda times pi 1 of x prime y. Okay? So, pi 1 of x plus lambda times x prime y is pi 1 of this, and hence the linearity follows. Okay? So the projections.
Excuse me, sir.
Yes?
Can you please go through that again? I'm a bit lost with pi 1, x plus lambda prime. Then you
See,
get.
what is pi 1 doing? Pi 1
yes.
is just extracting the first coordinate.
Okay.
Right? That's why I said it's pi 1. It's extracting the first coordinate. So if I have to show that it is okay?
Okay.
All right? So that's what I'm doing. Okay. You want me to be much more okay, let us do this in a much more explicit way. So remember V cross W is a vector space, the vector addition being addition in V in the first coordinate and addition in W as the second coordinate. Okay? So suppose I take xy and x prime y prime in V cross W. Okay? I have to show that phi 1, so I'm doing it a little more expanded way. Lambda times x prime y prime is phi 1 right?
It doesn't taken. No. It's one over.
Which one?
X prime is a derivative.
No, it's just another.
Not a derivative.
Yeah. It's just another member. Well, you eat an apple just as it is, but you don't eat a banana as it is. You feel it. Okay? So, before you don't get involved with symbols in that way. In derivatives, x prime is used to denote the derivative, but here there is no notion of derivatives. So, okay. All right. Yeah, that is one of the reasons why symbols turn out to be tyrannical, because you associate yourself much more with the symbol than what it is saying. Okay. All right. So I have to do this. So now let's expand. Phi 1 xy plus lambda times x prime y prime. So this is phi 1. So now let's evoke the operation in V cross W. Okay? So now, by my definition of phi 1, so this is x plus lambda times x prime, but x is nothing else but phi 1 times xy and lambda times y1 times x prime y prime. So that does it. Okay? So, sorry. And similarly, okay? So the projections are linear transformations. Okay? Now let's come up with another very nice example. Very generic, very nice. Okay. Okay? So, let me just draw the diagram, what I'm trying to do. So I have and then I have several linear transformations. Okay? You might ask, is this possible? That we have several linear transformations. Firstly, we have at least one. Okay? So, that's the first thing that I am going to show you, that I'm going to write it in this way. So what is this? I'm trying to speak about this set. So I'm trying to speak about the set which in purple, right? The set of all linear transformations from V to W. Okay? Given n, V and W are fixed. Okay? I'm going to speak about all possible linear transformations that might exist between V and W. It might be empty, I don't know. But still then, let's see. I'm going to show that it is never going to be empty, and it is much more. Okay. So this be the set of all linear transformations from V to W. Okay? So the question is, well, this could be empty, this could be non-empty, alright? So, the first one, it is not empty. There is at least one, I know. What is it? Zero, yes. The zero one. Well, what is it? This is the function which takes zero linear homomorphism. Okay? So this is the function which takes every vector to the zero vector. That's a function, right? Remember. So what is this? So this is a set, hom VW is a set, firstly of all functions from V to W which are further linear transformations. Okay? It's a set of functions. Now, I'm saying this function is there. It's a function. What's the extra property that it must satisfy to be there? It must be linear, right? It is there because, let's see, why? Then the reason is, okay, everything is yes.
So, if DW and DW are both vectors, so do we assume or we know that, or is it obvious that the set between D and W?
The set of all linear transformations. Yes, right? The set means set between V and W.
So that is obviously make it the set between D and W is a linear transformation.
Wait. What do you mean by the set between V and W? Set of what? Of? It's written, it's the set of all linear transformations from V to W. That's what I drew over here. Yes? This set contains these arrows, these linear transformations. Okay? That's precisely my, remember, to tell a set I must tell what is there. Okay? I don't know what you meant by set between V and W. So that's why I stopped you there. Is a set of all linear transformations from V to W. Okay? What is that? That means it's a set of all functions from V to W which further, each of them must be a linear transformation. Okay? Now, I'm saying that this set is always non-empty, whatever be V and W. Okay? So it at least has this function which I wrote like this, and I shall actually call this the zero homomorphism. Why do I say homomorphism? Now, I'm going to show that this is also a vector space.
What do you mean by offset?
I didn't make that name. Yes, these are called home sets. Huh? I think it was, I mentioned it somewhere in my notes. These are called home sets, but okay. Home sets because another traditional name of linear transformation is a homomorphism. Morphism means something which changes. Okay? Homo means of the same kind. Okay? A transformation of the same kind. So since this is the set of all homomorphisms, that's why it is called a home set. Okay? That's another name for it. Okay? But you need not. It's just a set of all linear transformations. Okay? I'm going to show that this is a vector space. with, so I have to give an addition. That means I have to give a binary operation on this set. So I take a pair of linear transformations and I'm going to give it this. I have to give this, right? I have to give this a binary operation. Okay? And how do I define this binary operation, f plus g? I mean to say this function f plus g. Well, I do the most obvious thing. I did it before. It's point-wise addition. It's just point-wise addition. Remember we did this before, in my last lecture. Okay? And what is my scalar multiplication? My scalar multiplication, it is this function. Again pointwise. Okay? Now, I'm saying this will be a vector space provided I can show that f plus g is actually a yes. Provided I can show that f plus g is a linear transformation as well as lambda f is a linear transformation. Let me say why. Remember the third way that I evolved, I showed you how to show that something is a vector space. You could obviously check all those things, you could check the associativity, commutativity and so on. But there's always an elegant way to do it. Okay? Yes. So what I'll do is, I will put this in a bigger one, which I will already know to be a vector space. Okay? So let's try that. So let's take that root. It's very, very similar, remember, to that exercise, where x was any set, and this was the set of all functions from x to r, which was shown to be a vector space. Okay? And remember, what was the addition over there? It was point-wise addition and point-wise scalar multiplication. And what I did when I did this example was to ensure that nothing special was taken about R. What I required was that R was a vector space. Okay? So the same thing tells me that if I replace this R by any vector space, W is the vector space that is also a vector space with point-wise addition and point-wise scalar multiplication. Okay? So that follows from that last exercise. So observe, for any set X, Further, what is this? This is the set of all linear transformations. So in particular, they are functions from B to W. Okay? So this is sitting already there. So you see that last exercise was so powerful. Okay? So it is sitting there. Okay, and we observe that the addition that was given in home VW is exactly pointwise. It's exactly the same thing that is there in this bigger one. So also the scalar multiplication, right? Okay? So it is enough to show. Remember, that was the way we showed that continuous functions on reals to reals are megavector space. How? Some of continuous functions in scalar multiples are continuous. It was exactly something similar, right? It was pointwise and so on. The same story, right? Okay? And remember, we have already showed that zero, that constant, that zero function, that zero map is already over here. Okay? And the zero map is the zero vector in W to the power B. Right? So that's the zero here. Remember, the zero map is actually here also. That's the identity. Okay? So I've shown that zero is there. If I take the sum of two, it is there. The scalar multiple is there. So one of the exercises which I showed, a subset of a vector space, that was the one, right? Which I'm using. Okay. So now, why should F plus G? So let, say, X and Y belong to V, and let me take lambda and mu from R. Now, firstly I look into F plus G of X plus mu times Y. Okay? Now, what is this? This is F of X plus mu times Y. This is the definition of but I know that F is already linear. So this is Fx plus mu times Fy plus, because F and G are both linear maps. Now I do my commutativity and blah 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 to actually regroup these things. Right? Okay? But what is this? This one again, by my definition of F plus G, is F plus G at X plus mu times. Okay? So this shows F plus G is a linear transformation. Clear? F plus G is a linear transformation. Clear? Okay. See, so very simple. We use is nothing but the basic axioms. We are playing this game. Okay? Clear? Okay. Shall I move on to the next one? I'll show this one. Huh? Okay. Okay. Now, the next one. Again, similar. This, by my definition of, but this, since f is linear, but then using the properties of the vector space, this is same as but this is nothing else but lambda times f of x plus mu times lambda times f of y. So they are linear transformations. So f plus g and lambda f are linear transformations. So we have shown that this is a vector space.
Second line.
Which one?
The second line. Yes.
Yes, because f is a linear transformation,
Yes.
so f of x plus mu y should be f of x plus f mu times fy.
Okay.
Yeah? That's why.
One.
Okay? So, see the parallel. It's very nice. We had sets, then we had functions between sets. Between any two sets, there was a set of functions from x to y. See, replace sets by vector spaces. We have vector spaces. Instead of functions, we now have linear transformations. Okay? So, we have linear transformations. We have, between any two vector spaces, the set of linear transformations that is also a linear transformation. That is also a vector space, right? So, see, the analogy is very much there, right? Okay? All right. So now, so we have, so what is this order? I think 8b. Okay? So we will show that this is a vector space. Now, so home this is a vector space. We have just now showed. All right? So this is also a vector space?
So can you just please go back one speed for a short moment,
Yeah. Okay? So home from V to W is a vector space. So if I have a vector space and two vector spaces P and Q, the product is also a vector space, right? So I have this to be a vector space. Okay? Now fix any A from B. So here is this map, which I'll write as A is not a good symbol. So what do I take? I take a linear transformation. No, I'll not do this. Sorry. So fix an A and so I take an F and I take it. So you can read this function as the evaluation at A. Right? So this is the function evaluation at A. Right? What are you doing? You're taking F, evaluating A. Obviously this is linear. So this is a linear map. Don't get bogged down by, so what do I have to do? I have to show this. Right? But let's see, what is this? This is a linear transformation. I have to evaluate this at A. By my operations, but this is the evaluation of F at A, and this is the evaluation of F at G. So done. As if the definitions were tailor-made to make this. Right? So evaluation at A turns out to be a linear transformation.
On the right hand side, the evaluation of A.
Evaluation of F at A. Right? So we call this map the evaluation at A. Right? Now, for the first time, I'm going to give a function which is, and we'll come back to this kind of functions. So, what is it? I take the pair FA and I evaluate it at A. And I just call it if. It's just evaluation, right? This is not linear. And I want you to find out why. So you come up with an example to show that this is not linear. Okay? Not linear, but for each fixed A and F, function is linear and the function this is linear. See, if I fix an f and I fix an 8, the evaluation is linear. Such maps are often called bilinear maps. We shall come back to this much later, near the end, but these are called bilinear maps and these are not linear. This is not linear. Okay? So this is one nice example. Before I end today, again, bringing up that analogy. So you had sets, functions, sets of functions, vector spaces, linear transformations, home. The linear transformations between two vector spaces, right? There's also another one. Composite of functions is a function, right? Over here, it is a trivial chain. If these are